Good morning, ladies and gentlemen. Myself, Hafiz Ahmed, lecturer, Department of Mechatronics Engineering, RUET. Along with me, we have Mohammad Mahfuz Raihan and Anab Tanjid as moderator to provide any sorts of technical supports to this session. Today, we are in the second of International Conference on Automation, Control and Mechatronics for Industry 4.0. Current time is 8:30 a.m. Bangladesh Standard Time. I would like to welcome all of you in the keynote session 5 of ACMI 2021. On this special occasion, we feel honored to have Professor Ian Petersen, Australian National University, Australia, as keynote speaker. ACMI 2021 has got new dimension to have a resourceable person like him. So, dear audience, this is time to welcome our honorable keynote speaker, Professor Ian Petersen, with big round applause.
Okay. So if you like, I can start now. So I'll start by sharing my screen.
Yeah, Professor Ian. Let me introduce you with your brief bio.
Thank you.
Thank you very much. Hafiz, can I go ahead with the rest of the task?
Ma'am, I need still 1 minute.
Okay.
Thank you for your appreciation. It's our immense pleasure to have Professor Dr. Celia Shahnas from Bangladesh University of Engineering and Technology as chair and Dr. Ziauddin from Usong University, South Korea as co-chair of this keynote session. After the end of the keynote presentation, there will be a question and answering session. All the audience are requested to write question if any in the chat box. Audience can also raise hand in Zoom after the end of the presentation. Now, I would like to request our honorable chair and co-chair to take the floor and introduce our honorable keynote speaker to the audience. Thank you.
Thank you, Hafiz. Thank you, Professor Ziauddin as my co-chair. Dr. Ziauddin, can I introduce Professor Ian with his biography? Okay, thank you very much. We are here with Professor Ian Petersen, Australian National University, Australia. And his keynote talk title will be Using Systems and Control Theory Ideas in the Design of Quantum Amplifiers. There is a lifelong experience from Professor Ian. I will just read a short one. Ian Petersen, a fellow of IEEE, was born in Victoria, Australia. He received the PhD degree in electrical engineering from the University of Rochester, USA in 1994. He's currently the director of the Research School of Electrical Energy and Material Engineering, the Australian National University, Canberra, Australia. From 1985 to 2016, he was with the University of New South Wales, Sydney, Australia, where he was a scientific professor and Australian Research Council lecturer fellow, laureate fellow with the School of Engineering and Information Technology. His main research interests include robust control theory, quantum control theory, and stochastic control theory. Dr. Petersen has served as an associate editor for the IEEE Transactions on Automatic Control Systems and Control Letters, Automatica, Siam Journal on Control and Optimization. He is currently an editor of Automatica. He was an Australian Federation Fellow. He is a Fellow of IFAC and the Australian Academy of Science. With that said, let us welcome Dr. Jan Petersen, and let us enjoy his keynote talk. If you have any question, as Javi said, write it in the chat box. Dr. Ziauddin will be helping you to handle the question answer session and do the rest of the work. Thank you. Welcome, Professor Jan Petersen. It's a great honor that we will be listening to you in this morning. Thank you very much.
Okay, thanks very much, Celia. And thanks very much for inviting me to give this presentation. So let's make full screen. All right. Okay, so this talk, as we've heard, is about using systems of control theory ideas in the design of quantum amplifiers. And it relates to an area of research that I've been working on for quite a few years now in the general area of quantum control theory. So this particular area of research is based on some joint research with some of my long-term collaborators, Matt James, also from the ANU, Valerie Ugranovsky from UNSW Canberra, and Naoki Yamamoto from Keio University in Japan. And in this presentation, as we can see from this title, we're looking at a particular problem in quantum systems and quantum technology, which is about quantum amplifiers and how systems and control theory ideas can be useful in this area. So the motivation for this research comes from developments in quantum technology and quantum information. And in particular, these developments, which are now becoming quite interesting and quite attracting a lot of attention, have motivated research in this broad area of quantum control systems, which is really about trying to develop a control theory for the case when the systems we're controlling are not governed by the laws of classical mechanics like Newton's laws, but rather are governed by the laws of quantum mechanics. So I guess the area that's attracting the most attention in this quantum technology area is that of quantum computing. And there's a number of technologies that are being used in building quantum computers, and also a number of very large companies such as Google, IBM, Microsoft have made significant investments in the construction of small-scale quantum computers. One of the important technologies that's being used here are so-called superconducting microwave circuits, which are based on cooling down microwave circuits to very low temperatures, millikelvin temperatures, and then constructing the quantum computer using the active elements, which are superconducting Josephson junctions. So, for example, recently Google, in its endeavors in this area, claimed to achieve what they call quantum supremacy with their technology, in that they claimed their quantum computer could actually solve a problem which couldn't be solved using a classical computer. Now, other companies working in the quantum technology and quantum computing area have disputed this claim, but still we are getting to the stage where quantum computing really needs to be taken seriously, and there's a lot of major companies which are doing that. Now, this talk is about some small part of that technology known as quantum amplifiers. And in the area of quantum computing, quantum amplifiers play an important role because the bits in a quantum computer, which are called qubits, need to be read out somewhere. So, for example, if you have one of these superconducting quantum computers where all of the computing is happening at very cold temperatures, and the signal levels at these quantum levels, so they're very small signals, we need some way of amplifying these signals and transferring the information from the quantum world, which is at this quantum computer operating at millikelvin temperatures, to the classical world, which is operating at room temperatures. So quantum amplifiers play an important role there. Another area where quantum amplifiers are important, or can be important, is an area called quantum sensing. So this is another aspect of quantum technology, and essentially it involves exploiting the laws of quantum mechanics to be able to detect or sense extremely small quantities. So an interesting example of this is the detection of gravitational waves. So within the last few years, it's been possible to detect these gravitational waves. They're extremely small deviations in the gravitational field, which have been detected using an optical method. Essentially, a very large optical interferometer has been constructed. This is the LIGO gravitational wave detection experiment, and that's enabled these extremely faint gravity wave signals to be detected in the presence of what's called quantum noise, which is a fundamental limit imposed by quantum mechanics, which limits how small the signals which we can detect are. So, as I said, the laws of quantum mechanics place fundamental limits on the signals that we can detect, but also how much we can amplify those signals. So what these laws of quantum mechanics tell us is that we can amplify very small signals, but when we do that, we of necessity need to add a certain amount of noise. The amplifier itself can only amplify the signal if a certain amount of noise is also added to the signal. And the amount of noise that needs to be added increases with the level of amplification that we need. So these limits have been derived quite a long time ago in physics literature using physics type ideas. But what we do in this presentation is look at the quantum theory of linear systems, the so-called quantum linear systems theory, and derive those limits on quantum amplifiers, and then also use this quantum linear systems theory to investigate the problem of designing quantum amplifiers, and in particular optimal ones, in the sense that they add the minimal amount of noise needed to achieve a certain amount of amplification. Now, the first problem we look at is the so-called phase-insensitive quantum amplifying problem. And these are amplifiers that provide amplification while maintaining what we call the coherent structure of our quantum signals. So we'll talk more about what a phase-insensitive amplifier is and what the structure that it preserves is, but it's essentially the property that we need to accurately amplify a quantum signal is this phase-insensitive property. An additional property that we also look at is the non-reciprocal property. And one of the problems in a lot of quantum technologies is that if we have an amplifier or a sensing device, that it causes back action. So the active amplification or sensing can affect the quantity which we're trying to measure or amplify. And so it turns out by properly designing a quantum amplifier using this non-reciprocal idea, we can eliminate to a large degree this back action effect. Okay, so as I said, our approach is based on the theory of quantum linear systems, which is really just an extension of our standard linear systems theory to take into account the limitations imposed by quantum mechanics. Now, in this quantum linear systems theory, we're looking at models, which are in some sense linear systems models. And to do this in quantum mechanics, we use what's called the Heisenberg picture of quantum mechanics. And so this was the picture of quantum mechanics invented by Werner Heisenberg, who's pictured here. And it's also equivalent to the alternative picture in quantum mechanics, which is the Schrodinger picture. Both of these are equally valid and essentially equivalent, but the Heisenberg picture is, in a sense, much more familiar to in control systems, people with control systems background, and in particular, it enables models which look very much like standard linear systems to be developed. So the idea of this Heisenberg picture is that the way we describe a system is looking at the time evolution of operators which represent variables such as position, momentum, voltage, or current. So just like normal state variables in a classical model might represent voltage or current, position or momentum or velocity, then in a quantum linear system, we still look at those quantities, but rather than representing them by real numbers, we represent them by these operators. So the underlying, if you like, unit or most basic model in a quantum linear system is the so-called quantum harmonic oscillator. So this is just like a normal oscillator, except it satisfies these quantum effects. And for these quantum harmonic oscillators, we can formulate a class of models called quantum stochastic differential equations. So in this Heisenberg picture of quantum mechanics, our models are inherently stochastic, which means they inherently involve noise. And in the Heisenberg picture of quantum mechanics, the uncertainty that comes from quantum mechanics, so this is Heisenberg's uncertainty principle, is represented by this quantum noise. And because of that, the models we have are these stochastic differential equations, but they're quantum versions of them. So in our models, rather than just having a single quantum harmonic oscillator, we can suppose that we've got a whole collection of them and they're all coupled together, and that would be our overall model. And in these models, we might have, say, n of these quantum harmonic oscillators, and because the variables involved are operators, they're actually operators on a Hilbert space. So we've got an underlying Hilbert space, and then we can have operators on this Hilbert space. And it turns out that a very useful collection of operators to look at are the so-called annihilation operators. So each one of these harmonic oscillators will have a corresponding annihilation operator. So if we have n independent quantum harmonic oscillators in our model, then we'd have n of these annihilation operators, and we can group them together in a vector. So we use this notation to say A is a vector, and that it's a vector made up of operators, so A1 up to AN. Each one of those operators is an operator on the underlying Hilbert space, and we group them together in a vector. So this is going to behave very much like the state vector in our normal linear systems model, but rather than the elements of the state vector being just real numbers that evolve with time, now they're operators that evolve with time. And it turns out each of these annihilation operators is an unbounded operator on the underlying Hilbert space. Okay, so what do these models look like these linear systems models? Well, they look very similar to standard linear systems or standard stochastic linear systems. So what we've got is a set of differential equations or stochastic differential equations where the variables are these annihilation operators, but also we've got the adjoints of these annihilation operators are the so-called creation operators. So we missed this slide about creation operators. So if we've got a vector of annihilation operators, then if we take the adjoint of each of those operators, we'll get another vector of operators, which we use the notation A hash, and each one of these operators are called the creation operator. So it turns out that in quantum mechanics, variables almost always come in pairs. So in the case of these annihilation operators, we have the adjoint of the operators which are creation operators, and we always have both annihilation and creation operators. And physically, what these annihilation creation operators represent, it actually corresponds to the name, they represent the annihilation and creation of a photon. So that's where that name comes from. And some more notation, sometimes we use row vectors of these operators. So we use the transpose of the A vector. And then we can combine that with the adjoint to get this dagger operator, which means the adjoint transpose, which is a row vector of creation operators. Another bit of notation we often use is this doubled up notation. So often matrices we deal with are complex matrices and have this particular form. We might have two blocks, R1 and R2, which are both complex matrices, and then we repeat those blocks down here to get R2 hash, which in this case, when we're talking about complex matrices, just means the complex conjugate transpose and R1 hash complex conjugate. Sorry, just the complex conjugate. And the notation for that, we use this delta R1, R2 to represent that matrix. The other matrix we often look at is this J matrix. It's just a real matrix which is made up of the identity matrix and minus the identity matrix. And it turns out that this comes up a lot in this quantum linear systems theory. So we'll come back to that quite a lot. So continuing on with our quantum linear system, we've got these quantum stochastic differential equations, which look very much like linear stochastic, ordinary stochastic differential equations, where these A, B, C, and D matrices are just complex matrices. So the variables here are operators, but these coefficients in the model are matrices, but they're complex matrices rather than real matrices. And it turns out these matrices always have this doubled up form. So in this model, we've got an input U, which represents the electromagnetic field acting on the system, or it could be the quantum noise acting on the system. And then we have an output Y representing the corresponding reflected field from that incoming electromagnetic field. So it's like if you shine a laser on an atom, then it'll reflect back. So the input will be the laser coming in and the output will be the reflected beam coming from that laser. Now, the inputs and outputs are also operators. So they're like these annihilation and creation operators. And again, they always come in pairs. So all these quantum signals always come in pairs, such as annihilation and creation operators. So the dimensions of our system are always even dimensioned because everything always comes in pairs. Okay, so it turns out that if we look at these models, not every matrix A, B, C, and D does that represent a real quantum system in terms of a system for which the laws of quantum mechanics would be obeyed and for which we could actually build such a system using quantum mechanical devices. So that leads us to bring in a notion of what we call physical realizability, which tells us when such a model is physical. It represents a real physical quantum system. And the definition of this relates to an underlying Hamiltonian for the system and a coupling matrix for the system. So Hamiltonians are often used in lots of areas of physics to describe system dynamics, and in particular in quantum mechanics. And in this case, for these quantum linear systems, the Hamiltonian describing the system can be described in terms of a complex matrix, which is Hermitian. That's what that notion means. And also another complex matrix, N, which defines the coupling between the system itself, which may represent, say, an optical cavity or an atom, and the external electromagnetic field, which might be a laser beam acting on the system. There's a final matrix S, which is a unitary matrix, which represents the scattering or cross-coupling between the different inputs and outputs of the system. So these three matrices will define a physical quantum system, and they'll also define corresponding matrices A, B, C, D in our previous linear state space model. So physical realizability is simply saying that our A, B, C, D can be represented in this form for some matrices M, N, and S. And in that case, we've got a physically realizable quantum system, and we could actually build that out of quantum components. So this is really the state space definition of physical realizability. Because we're dealing with linear systems, we can also look at the corresponding transfer function matrix. So that's what we've got here. Given matrices A, B, C, D, which can be complex matrices, we can define the transfer function of that system in the usual way. And then if the underlying state space model is physically realizable, then the transfer function is said to be physically realizable. So a given transfer function is physically realizable if it's the transfer function of a physically realizable linear quantum system, which is like a state space model. So we'll be in this discussion of quantum amplifiers, we'll be mainly actually talking about transfer functions. So rather than have to find these Hamiltonians, coupling operators, etc., we'd like to have a test to know whether a given transfer function is physically realizable. And it turns out that the following theorem has been established by myself and other collaborators and people working in this area, which says that a transfer function is physically realizable if and only if the following property holds. So this is what's called the JJ unitary property. J was that matrix I mentioned before. It's the 1, 0, 0, -1 matrix. G is our transfer function. That's J again. And G tilde is the adjoint transfer function, which is defined in this way. So if this equality holds for all frequencies S in the complex plane, and then we've also got this additional condition that at infinite frequencies, our transfer function must be of this form here, where S is a unitary matrix, then that's equivalent to the transfer function matrix G being physically realizable. So what we're going to try and do is construct a transfer function matrix for our quantum amplifier, which is physically realizable, because we need to be able to build our quantum amplifier, and so it would need to satisfy this condition. So, and that the reason we can build it is because the corresponding system satisfies the laws of quantum mechanics, and then we could build it with a suitable technology. So we'll sort of look at two main technologies that might be used to build these quantum amplifiers. One is quantum optics, which is used in some versions of quantum computing, and also it was used in the gravitational wave detection problem. And the other technology we'll look at in some cases is the superconducting circuits case with the Josephson junctions, which is used in these main experiments on quantum computing. Turns out the optics case is a bit easier and a bit easier to understand. The circuits one is a bit more difficult. Okay, so the first problem that we're going to look at is this phase-insensitive quantum amplifier. And the idea is that we want to amplify a signal, but all of our signals have these two components or quadratures, such as the annihilation and creation operator. Quantum signals always come in pairs. And so the phase-insensitive property is that when we amplify a signal, we want to amplify both components of these of the signal equally, so that we preserve like the ratio between the two components, and that's preserving the coherent properties of the quantum signal. So if we have such an amplifier, it's called a phase-insensitive quantum amplifier, and we want to construct such an amplifier to add the least possible amount of noise to the signal when we do the amplification. So we'll derive what is the least amount of noise that we need to add, and also how we can construct an amplifier which actually achieves that, and also achieves the required gain that we're looking for, and also the required bandwidth. So the approach that we look at is really just to concentrate on a single frequency, which we can assume without loss of generality is DC, the zero frequency, and then use a singular perturbation type procedure to construct an amplifier which has the right properties over some frequency range out to some given frequency or bandwidth. And in the optical case, which is the simplest case, what we can find is that we can solve this problem with an amplifier using some quite simple optical devices, two what are called squeezers, which are the active devices in quantum optics. They give us the amplification, and two beam splitters, which are passive devices, which just perform the required interconnections. Okay, so it turns out that a phase-insensitive quantum amplifier requires two input channels and two output channels. So in this case, the input channel Sin represents the signal that we're trying to amplify, and the corresponding output channel to that would be the amplified version of that signal. So in the case of these quantum systems, often when we draw signals in a line with each other, that means this output is the one that the corresponding output to that input. So for example, if we shine a laser beam into our atom and it's reflected out, then this is the corresponding output of that. Now, because we can't achieve this quantum amplification without adding noise to our signal, then we need to have a second channel, which is the noise input. So this will be just what's called vacuum noise. So it doesn't have any signal on it, it's just noise, but it needs to be there so that the laws of quantum mechanics are satisfied. And we're trying to make sure that not too much of this noise signal gets on our output signal. Now, because every input signal has a corresponding output signal, there'll be this corresponding output signal here, but we don't actually use that. That's just included there to be consistent with our theory about physical realizability, that the system is square, that for every input there's a corresponding output. Now, all of these signals actually have two components, an annihilation creation component. And so really our transfer function will be rather than a 2x2 transfer function, will be a 4x4 transfer function. So we've got these two components. The transfer function that we're trying to synthesize is a 4x4 transfer function matrix corresponding to the 4 components on the input mapping to 4 components on the output. And it should be physically realizable, so we can actually build the amplifier and also satisfy the required gain that we're trying to achieve in our amplifier. And it should have this phase insensitivity property that it amplifies the two quadratures of the signal equally over the specified frequency range. So we can expand out our input and output signals into the 4 quadratures. So if you like, this is our input signal Sn. This is like the annihilation version of it. This is the creation version of it. And then our noise input is this one, and our annihilation version is this, the creation version is that. And if we expand this out in this way, then the transfer function matrix G will also have this doubled up form like this. So there's really only 2 transfer functions, which are 2x2, this G and this G, which we need to construct. So we need to construct these 2x2 transfer function matrices, and each one of the components of those 2x2 transfer function matrices will be a scalar transfer function. So these are the 8 transfer functions that we have to construct, and they have to meet the constraints that correspond to the phase insensitivity, the gain, etc. Okay, so let's look at what those constraints are. So the first one is the phase insensitivity constraint. So suppose we're looking at a frequency omega where we want our amplifier to have this property, then the phase insensitive property is that the H11 element should be 0. So let's go back to the previous one. So that means this element here should be 0, and this element relates to how much of the quadrature, the creation part of the signal crosses over into the annihilation part of the signal. We don't want any of it to cross over because we want it to maintain phase insensitivity, so we want that H11 to be 0. The next part is about getting our required gain. So this is how the signal input maps to the signal output. And that should give a corresponding gain G, which is the gain that we want to achieve. In general, G could be a complex number at the frequency omega. So because we're mostly going to work at DC, as I mentioned, normally we'll drop this J omega condition and just assume that everything is at omega equals 0, and then we'll talk later about how we can extend that to a desired bandwidth. So also we've got to think about the noise acting on our signal, that the amount of noise, if you like, the amplitude of the noise energy would be given by this quantity here. It's equal to the magnitude of that G12 and the magnitude of that H12 squared. So that's G12 here and H12 here. Both of those components represent the noise input acting on the output signal. So we want to minimize that at a given frequency, again, usually the DC frequency. Okay, so our main result is essentially telling us how much noise we need to achieve a certain amplification G. And the result is this formula here. So it says the minimum amount of noise that we need to add on to our amplified signal, which is expressed in terms of this quantity here, is given by this formula here. So it's essentially the gain squared minus 1. So as the gain goes up, we need to add more and more noise to our signal to achieve that amount of gain. And here we're taking the minimum overall transfer functions, which are physically realizable, achieve the phase insensitive property, and achieve the required gain. And we're really restricting attention to the case when G is greater than 1, which corresponds to an amplifier. You can get a corresponding formula for the case when G is less than 1, when we've got an attenuator. There's also limits in that case, but we'll concentrate on the amplifier case. So this theorem also tells us actually a class of amplifiers for which this property is achieved. So as we've said, the amplifiers are characterized by these two 2x2 transfer function matrices, and they're dependent on this parameter G, which is how much gain we want, and also dependent on another real parameter mu, which is just a free parameter. It turns out there's not a unique solution to this problem. We've got some freedom in this parameter mu, which we will use later to look at various physical realizations. But in general, just to achieve physical realizability, we've got a whole class of amplifiers which can achieve what we want and achieve this minimum amount of noise given by this formula here. So that's our main result in this area. And then we want to see, well, we know how much we can achieve. We know what the transfer function is, but how could we actually build such an amplifier? And we'll mainly be talking about the optical case. And to do this, we'll use this following well-known result, which occurs a lot in quantum mechanics literature, known as the shale decomposition. So essentially it says, given any 4x4 complex matrix, which satisfies the physical realizability condition, which is this JJ unity property, then we can decompose it in this way here. where R is a diagonal matrix, which is real, and S1 and S2 are unitary matrices. Now, because this R is diagonal, this term here actually corresponds to the amplification part of our amplifier, and the diagonal property means we can break our amplifier down into two scalar amplifiers. So our overall system has got 2 input channels and 2 output channels, but we'll break it down into 2 single channel amplifiers, if you like, with amplification corresponding to these constants R1 and R2. And then these unitary matrices S1 and S2 in these terms here correspond to the sort of coupling between the input signals and output signals and our 2 amplifiers. So these in optics will be represented as beam splitters, whereas these terms here, the amplification terms, will be represented in what's called a squeezer, which is a simple one-channel optical amplifier. So this theorem enables us to decompose our problem from a 2x2 problem into 2 one-channel problems. And so next we'll look at how we can realize these single channel amplifiers using what's called a squeezer. The unitary parts, as I said, could be physically implemented using beam splitters. And since these matrices S1 and S2 are both 2x2 matrices, it turns out that they can be implemented by just a single, each can be implemented by a single beam splitter. So a beam splitter is, in the optical case, is simply a partially reflecting mirror. And if we have 2 input beams coming to either side of the mirror, then the corresponding output beams will be related to the input beams by a relationship like this. It's just a linear relationship. And this matrix R here is a unitary matrix, and it has this particular form where these parameters, the parameters of the beam splitter. And it turns out that any 2x2 unitary matrix can be represented in this form R. So that means that our input and output matrices here can be represented each by their own beam splitter. Okay, so that next goes on to our amplifier part. And now we'll assume here that R is just a scalar. So we're just looking at each amplifier individually, and we're going to synthesize these using what's called a single channel dynamic squeezer. So a single channel dynamic squeezer can be built in optics using a collection of mirrors, one of which is partially reflective, and also it needs to have a nonlinear optical element inside the cavity. So we build this cavity out of these mirrors, and then inside we put like an optical crystal, which has this nonlinear behavior, which gives us the amplification. So even though the theory we're talking about is all linear theory, it turns out that to achieve amplification, we need a nonlinear element. But because the nonlinearity is typically very small, then by suitable linearization approximation, we can get a very accurate model which is linear. And this is the QSDE model for such a squeezer, which we can obtain. So it's a single harmonic oscillator model. It's got a single annihilation operator. Kappa is like the damping in the system. It represents how much signal decays out this partially reflected mirror when it goes in and out. U is the input, so the input, say laser beam coming into the cavity. Y is the reflected beam. And then chi here represents the linearized nonlinearity, which is, if you like, the amplification term. It's actually a complex number, and the bigger chi is, the more amplification we can get. So to get a full linear systems model for such a squeezer, we need the dynamics of the annihilation and the creation operator. So it's a 2x2 dynamics. Again, we're always dealing with even numbers in our dimensions. And so we get this model here. We get the pair of inputs and the pair of outputs. And one thing that's important for our amplifiers that should be stable, and we can just use normal linear systems theory. This matrix here needs to be Hurwitz, which corresponds to this condition here. Essentially, we need enough damping to counteract the amount of amplification so that we don't get instability. So we'll assume that we've got that. We have a stable amplifier, and this is a schematic diagram for what it would look like. So we've got a reflecting mirror, a nonlinear material, and a partially reflecting mirror, the input beam, the output beam, and then that overall makes our squeezer. So if we look to analyze this to see that we get the right property, we need to do some change of variables and essentially apply this singular perturbation approach. So doing that, we can rewrite the dynamics of our squeezer in this way and calculate the DC gain of the squeezer, which is this quantity here. This gives us the transfer function matrix for our squeezer in terms of the ratio between chi and kappa. That remains the same with this change of variables. And so we then actually get the following result, that given any matrix of this form, there exists such a squeezer which gives that matrix. And with a ratio less than 1, so all these things are well defined. And then this singular perturbation parameter can be chosen so that that DC gain continues out to any desired bandwidth. It won't be exactly at the DC gain value for the higher values of frequency, but almost will hold, and we just need to change this parameter to get any bandwidth we want. In practice, there's technological limitations on how high a frequency our nonlinear crystal will work. So in theory, quantum mechanics says we can have any bandwidth, but in practice, it will depend on the technology we're using. Okay, so then this gives us really our main result, which is that for any gain G, we can design such a quantum amplifier to achieve that gain, and then we can choose the parameters to give any bandwidth as well. And we can construct it from 2 beam splitters and 2 squeezers. And this would be a kind of schematic diagram of what it would look like in optics. So we've got the 2 squeezers, the 2 beam splitters, the signal coming in, signal going out, the noise coming in, and this is the behavior. So if we wanted to do a corresponding thing in the microwave case, then we'd need like a microwave version or a Josephson junction version of our squeezer. Turns out we can do that, but the signal coming in has to be exactly the same as the signal coming out. So it's like the optical case would look like this. And that actually puts a significant restriction on what we can achieve. So in the optical case, that would mean we're restricted to a signal like this, where we have a single beam splitter which operates both for the input and the output. All the signals go both ways in this case. So the restriction is then that we have to use the same squeezer for both the input and the output. Now, it turns out that you can do that if we choose our parameter in the right way. So the corresponding microwave case would look like this. And as I said, it turns out we can do that by choosing that parameter. We had that mu parameter. If we choose that 0, then this does work. We can use the same squeezer in both the input and the output and still get exactly the same amount of noise. And interestingly, in this case, our transfer function becomes a symmetric transfer function. So that's the solution for the phase insensitive problem. I'm just about running out of time to look at the non-reciprocal version of it. I'll just very quickly set up the problem. In this case, we change our setup slightly. We want to have our signal coming in goes to a different channel in the output, because we don't want to have any of the signal coming in reflected out the same channel, because that would be this back action. So we choose a different channel for our signal output. And it turns out in this case, we then need to have an extra noise channel to obey all the laws of quantum mechanics. So the problem becomes more complicated. We need three input channels, 3 output channels, and each channel has 2 quadratures. That'll be a 6x6 transfer function matrix we're trying to construct. So 6 inputs, 6 outputs. We can go through a similar procedure. First of all, writing down all the coefficients, all the conditions we need to satisfy for the phase insensitive property, the non-reciprocal property now, the gain property, and the noise. And then it turns out we can solve this problem as well. And actually, we don't need to add any extra noise in this case. So we get the same formula for the noise. Our transfer functions are more complicated now. They're 3x3. And we're only giving actually 1 transfer function here. But again, there's a whole class of them that actually work. And in the optical case, we can again apply the shell decomposition, but things are quite a bit more complicated now. We need 3 squeezes, and then these S1 and S2 are 3x3 matrices, which means we actually need 3 beam splitters for S1 and S2. So that's like 6 beam splitters altogether plus 3 squeezes. So it's quite a bit more complicated, and but still gives us the same level of performance. So I think I'll stop there to allow time for some questions. So the conclusions are that we've used quantum linear systems theory to design these optimal amplifiers based on this idea of physical realizability. We found that we can actually solve this problem, that we can construct an amplifier which contributes the minimal amount of noise. Quantum mechanics imposes restrictions on the noise, but not the bandwidth. But there will be technical issues about constructing the bandwidth. In the phase insensitive case, we could extend to the microwave case. In the non-reciprocal case, we could solve the problem as well, but we haven't really been able to solve the microwave case in that case yet. So I'll stop there and allow time for questions.
Thank you, Professor Petersen, for your wonderful talk. I hope all the audience who are interested to know about these topics, that would be surely helpful from your talk here. So I would like to actually invite all the audience. If you have any question, you may ask. Yeah, Professor, Doctor. So please. I cannot see. Okay, yeah. Krishna, Ajoy Krishna, Professor, can you? You can ask the question here. Professor Ajoy Krishna.
Sure.
Yes.
Sir, please unmute yourself.
I'm sorry, it was muted actually.
Yeah,
thank you very much for your nice presentation. I am interested in actually if we use a Josephson junction, so we need to very low temperature. So what critical temperature for superconductor we can achieve to use at a room temperature? What is the superconductor temperature, critical temperature we could have right now, the maximum?
Well, I mean, for superconductors, it has to be. It's like I think it's like about 4 degrees Kelvin. But for these quantum amplifiers to work, it has to be much colder than that. So that so that, as I said in the introduction, has to be millikelvins. So that's like 1,000th of a Kelvin. So they use special optical cooling, laser cooling, to get down to those really cold temperatures. So the reason is because at microwave frequencies, the noise goes up with temperature, and to get down to the noise levels where we only have quantum noise, not what's called thermal noise, we have to get down to these very cold temperatures. But it turns out that at optical frequencies, to get down to the quantum noise limits, we can actually work at room temperatures. So it's the fact that we have to get down to these really low temperatures is related to the fact that these technologies work at microwave frequencies rather than optical frequencies. But at optical frequencies, there are other difficulties, that it's much more difficult to make amplifiers and quantum devices than at microwave frequencies. So at microwave frequencies, we can make things like quantum computers and quantum amplifiers using these Josephson junctions. We don't really have anything like that at optical frequencies, but we have these optical crystals, but they're much more difficult to achieve any amplification and any sort of quantum computing effect. So it's sort of a trade-off. So for the moment, it seems like in terms of the quantum computing technology, the microwave technology seems to be the most effective at the moment, but then other groups are working on the optical technology, and so it's not clear which one will be better in the end.
So you're telling that microwave technology could be more promising in case of, quantum fabrication, you are telling us.
Yeah, the microwave technology seems to be able to scale better, so they can make much bigger quantum computers at the moment using the microwave technology. So they've got maybe 100 qubits at the moment, but people using optical technology, I think, have not been able to make more than 2 or 3 qubits. So at the moment, the microwave technology seems much more scalable, but it does involve all of this cooling. So like these quantum computers are huge because of the cooling requirement. If we went back to...
Yeah, I got it. Thank you very much for your answer.
Yeah, I'll show you the picture of the quantum computer, that they're huge things.
Okay, thank you, Professor. So if you have any question, you may ask. Is there anyone to ask the question? Maybe you don't have any question. Actually, although the field is a little bit different than me, okay, I want to ask a general question. Okay, just curious to know about the future of the quantum computing, okay, over the traditional. Can you tell us some future scopes? Yeah, what is the future?
Yeah, I'm not sure I really know the future. I mean, I guess I'm kind of a bit surprised that it's been so successful so far. I kind of thought it was a much harder problem than it seems to be. But I guess with companies like Google and Microsoft and IBM, they have a lot of resources they're putting into it. But I still really don't know how practical it's going to be. It's I mean, it seems to be getting to the stage where there are some very specialized problems that these quantum computers, these companies have made can actually solve, but I'm not sure how long it will take before they can solve lots of problems, and where they'll be really useful for the amount of money that it costs. So it's a tricky question, but I think there's certainly a lot of interest in it, and a lot of people are doing research on it. So I think there's a chance that it will become useful, but you never really know with this sort of stuff.
Yeah. Thank you, Professor. Yeah, thank you.
Yeah. Thank you.
Yeah, as we don't have any question, we want to stop here, and thank you again for your hard work and best effort for this conference. Yeah, and yeah, I want to, actually this is the end of the session. I want to transfer the session to the Professor Shozal. Okay. Professor Shozal, thank you, Professor Shozal, for inviting me, okay, to as a co-chair in this session. Yeah, thank you. It's a wonderful talk.
Thank you, Dr. Ziauddin, for being with us as a session co-chair for this session. Professor Ian Petersen was my supervisor, so it is my honor to have him as a keynote speaker in my session. And this conference has got a new dimension truly with the addition of Professor Ian Petersen. He's one of the genius in the field of control systems and system theory. So Hafiz, I would like to request Hafiz to proceed from now. Hafiz, would you like to share, please?
Thank you, sir. At this stage, I would like to request the organizing chair, ACMI 2021, Dr. Sajal Kumar Das, to hand over a certificate as a token of appreciation to our keynote speaker, Professor Ian Petersen.
This is a different one, Hafiz.
Okay, thank you.
Hafiz, get the correct certificate.
Yeah, got the right one.
Enough.
Stuff. Yeah. Okay.
Okay, and this
Sorry,
is
sir, for the disturbance.
yeah, this is a digital certificate. Please accept it from us, as you are not physically here. We'd be happy if you could accept this certificate as a token of appreciation.
Okay, thank you very much. Yeah, it's been my pleasure to present this presentation and this conference. So thanks again for inviting me, and thank you for the certificate. So, and I hope the rest of the conference is very successful.
Thank you, sir. Ladies and gentlemen, it is time to appreciate our honorable session chair and co-chair. Now I am requesting the organizing chair, ACMI 2021, to hand over a certificate as a token of appreciation to the chair of this session, Dr. Celia Shahnaz, as I know she is currently absent.
Okay, Dr. Ziauddin, would you like to receive this certificate on behalf of Professor Dr. Celia Shahnaz as a co-chair of this session? So
thank you. Yes, thank you. Thank you for giving us the opportunity.
Thank you, sir. Now I would like to request our organizing chair, ACMI 2021, to hand over a certificate as a token of appreciation to the session co-chair, Dr. Ziauddin.
Dr. Ziauddin, please accept this certificate as a token of appreciation. Thank you for being with us.
Thank you, Professor. Yeah, it's wonderful to work with you. Okay, and hope to work in future days. Okay. Good luck for you, this conference as well as the future conference. Yeah, thank you.
Thank you, Honorable Session Co-Chair. Ladies and gentlemen, it is time to capture this beautiful memory as a source of inspiration for the next edition of this conference. I would like to request all of you to open your camera to complete the photo session. Please have a photo session. Dear audience, please turn on your camera for photo session. Thank you all for your participation in this session and make this session live. With the permission of the co-chair and the organizing chair of ACMI 2021, I would like to close this session. Thank you again.
Yes, thank you all. Okay, thank you.
Okay, thank you, Ian, once again for joining us, and hope to see you in the next version of the conference as well.
Okay. Thank you. Have a safe life, dear. Thank you.